Today we will discuss the radioactive decays. As you must already be familiar with radioactive decays of nuclei. There are many nuclei that is found in nature which decay over time, converts itself into some other nuclei, and artificially also we could make nuclei decay into other nuclei. So, in this discussion we will consider some aspects of this radioactivity of the nuclei. So, the examples of radioactive nuclei are uranium, which has 92 protons. It can undergo what is called the alpha decay by emitting helium nucleus and converting itself into thorium, which has 90 protons in it. Another example is uranium again 90 to 237, which emits negatively charged particles, in fact electrons, and the Z number in this case goes up by 1 unit, becomes 93 from 92. Okay, and that is another example. Then there are many nuclei which, when they are in excited state, emits photons, gamma rays, and converts itself, comes down to de-excites by emitting this photon. So, the first one is an example of alpha decay, because this helium nucleus is called alpha particle, and the second example is an example of a beta decay. So, the emitted particle is called beta particle with negatively charged particle. We will see that this negatively charged particles are nothing but electrons coming from the nucleus. Sometimes similar to the particle similar to electron comes out, but with positive charge. In fact, they are the antiparticles of electrons, which are called positrons. So, this positron emission is called beta plus decay. For example, krypton with 36 protons emits positron, and its Z number now comes down by 1 unit to become 35 bromine. And the de-excitation and emission of photons is called gamma decay. And another process that can happen is, apart from the nucleus, in the atom there are these atomic electrons. So, the nucleus sometimes captures, absorbs one of the low lying electrons which are moving around the nucleus in an atom. Say for example, if you take beryllium with 4 protons and 7 neutrons in the 7 mass number, which means 4 protons and 3 neutrons in the nucleus, has 4 electrons moving around in the beryllium atom around the nucleus. Now, this neutron, so the nucleus can capture one of these electrons and thus reduce its charge by 1 unit. Okay. So, the Z number is reduced by 1 unit, and so it becomes a lithium nucleus with 3 protons and 4 neutrons. We will see later that it actually converts one proton in the nucleus by absorbing an electron to neutron. We will come to the details later. This particular kind of reaction process is called the electron capture. So, these are the basic spontaneous activity that can happen in an atom, and there are many such atoms which exhibit these decay properties. The alpha and beta decays are followed by gamma ray emission, which means that the nucleus produced by alpha or beta decay themselves are actually in an excited state, and they further decay down to the ground state by emitting gamma rays. You can ask a question like, when we discussed the atomic models earlier, we had discussed some nuclear potential and discussed the energy levels, different energy levels possibly occupied by the nucleons. Say for example, in the shell model we considered Woods-Saxon kind of potential, and then we could solve the Schrodinger equation, get the energy states of the nucleons. These are stable states. So, such states cannot actually decay, they are there, their lifetime is infinite. So, they are there for infinite time. So, in order to, how does this decay happen then? So, for such spontaneous decay, the nucleons should be, or some of the parts of some nucleons should be experiencing some time varying potential with this. So, this time varying potential is needed to, time varying part of the potential is needed to understand the quantum mechanics of spontaneous decay. We will not go into the quantum mechanics of the spontaneous decay, but rather we will consider some common properties of the radioactivity itself, basically mostly derived from experimental observations, etc. So, let us look at some of the common properties of radioactivity. Basically, there are observations, large number of observations which are made on radioactive nuclei, and then we understand a lot about the common properties that such decays follow. These properties are mostly independent of what type of decay that follows. For example, whether it is alpha decay or beta decay or gamma decay, the decay properties, some of the basic properties of the decay, rules that the decay process follows are independent of what type of radiation happens. One thing that we know from experiments is that the number of decays depends on the amount of material that is present. What does that mean? It means that if you look at the decay rate, say let me call this the activity. So, this is basically the rate of decay. It is observed that this activity is linearly proportional to the number of nuclei. the number of nuclei present in the sample. So, I can actually write down equation relating the activity and which is basically the rate of decay, okay, or the rate at which the number of particles come down, dN by dt. Actually, the modulus of that, just the magnitude, is equal to some constant times n, where n is the number of particles present in that, number of nuclei present in that. And the lambda is called the decay constant. Decay constant. If you take one particular atom, there is, consider it in this fashion, there is one nucleus, radioactive nucleus. It has some probability to decay. If lambda is the probability to decay, if you take n such atoms, such nucleus, then lambda times n is the number of particles that will decay in 1 second. So, if lambda is the probability per unit time, per unit time, okay, probability per unit time of decay of one nucleus. So, if you have 1000 nuclei and lambda times 1000 is the number of nuclei that will decay in 1 second, if lambda is expressed in term per decay per second. So, that will tell you the unit of radioactive activity. Okay. So, the activity unit of A is decay per second. There is another commonly used unit called Curie in honor of Marie Curie, who has done a lot of work in radioactivity related science, and she has won 2 Nobel Prizes also for her work in radioactivity. So, Curie, which is denoted as Ci, is basically defined as 1 Curie equal to 3.7 times 10 power 10 decays per second. Okay, so this also tells us that radioactivity is a kind of a statistical phenomena, which means if you take a particular nucleus, you cannot say when it will decay or how long will it live there without decaying. What you can say but is, if you have 1000 such nuclei, how many of them will decay in 1 second or 1 minute or some interval of time. All right. So, basically this kind of probabilistic nature is a common property of quantum mechanical processes. So, there is no surprise that radioactivity also has is statistical in nature. So, we said dN by dt, the rate of decay is proportional to n, and in fact, we said it is equal to lambda n. The absolute value was lambda times n. So, if we take lambda as positive, like probability should be positive. So, it is a positive quantity, n is also a positive quantity, but we know that dN by dt, the rate actually decreases as time increases for some short time interval dt. The number of particles will actually come down. So, dN by dt is a decreasing quantity. Okay. So, it should be minus lambda n. Okay. So, this negative sign actually says that the number of particles decreases with time. All right. So, now we can try to get an expression for this. I will rewrite this as take the n to the left hand side and write it as dN over n, which is now equal to minus lambda times dt, which goes to the other side. Integrating, we will get say t equal to 0, we will switch on at time t equal to 0 and then ask the question after some time t what happens. So, integrate this from 0 to t, corresponding n value, and let us consider denote it as n 0, which is the number of particles present at t equal to 0, and n t is the number of particles at time t. So, left hand side limits of integration are n 0 to n t, and right hand side it is from 0 to t. And left hand side, when you integrate 1 over n dn, you will get logarithmic log n within the limits n t and n 0, it will come out to be log of n t over n 0 equal to the other integration will give you minus lambda, which is a constant which is taken out. Integral dt is t within the limit 0 to t will give you t, simply t. So, now you take the exponential on both sides, okay, exponentiate this. Exponent of log is whatever that quantity n t by n 0 is equal to exponential minus lambda t, or you can write n t equal to n 0 times e power minus lambda t. So, this is basically the familiar exponential law of radioactivity. All right, some consequences of this. So, we have n t equal to n time t is equal to n 0 exponential minus and if in particular we take t to be equal to say some t half, let me denote t equal to t half as some particular time, and n t half. So, t half is such that n t half is equal to say n 0 by 2. So, we started at time t equal to 0, we had n 0 particle nuclei, and after t half time we have n 0 by 2 particles or nuclei in the sample. But according to the exponential law, this is related to n 0 as n 0 times exponential minus lambda t 1 by 2, right. Both sides we have n 0. So, we can actually divide by n 0 on both sides, and you will get 1 over 2 equal to exponential minus lambda t by 2, or invert this, take 1 over on both sides, you will get 2 is equal to exponential plus lambda t half. Now, we take the logarithm on both sides. So, that will give you log 2 is equal to lambda t half. This time needed to reduce the number of nuclei from N0 to N0 by 2 is called half life of that particular nucleus. So, half life t half is equal to logarithm of 2 divided by the decay constant lambda, which log 2 can be written as 693, okay, truncating it up to third decimal place divided by lambda. Okay. So, half life is a measure. So, this is a probabilistic this thing. As we said, we cannot talk about the time that one particular nucleus will stay alive, but in a sample we can say that the number of the time taken by the sample to reduce its number or amount by half. This is called the half life of the sample. So, that is equal to logarithm of 2, natural logarithm of 2 divided by the decay constant lambda. All right. So, as I said, it is statistical in nature, not possible to say when a particular nucleus will decay, but can predict how many nuclei will survive or decay after a particular interval of time. We can also define what is called the mean lifetime, which is essentially the average time of the lifetime of the nucleus, which is defined as tau, which is equal to integral 0 to infinity t dn by dt, the rate at which it will decay times the time interval around the time t divided by integral 0 to t dn by dt. If you wait up to infinity, so this can be written also as 0 to infinity t dn by dt is nothing but lambda n dt divided by 0 to infinity lambda n dt, okay, is equal to integral 0 to infinity t lambda n at time t is nothing but n 0 times exponential minus lambda t exponential law into dt divided by 0 to infinity lambda n 0 e power minus lambda t dt. So, if you do the integration, we will leave it as an exercise for you. The numerator will turn out to be n 0 over lambda, simple integration. You can use integration by parts, and the new denominator is obviously lambda n 0 are constant, okay, and then integral e power minus lambda t dt from 0 to infinity will give you 1 over lambda. So, this will simply give you n 0, and therefore, the whole thing is just 1 over lambda. So, we can say the mean lifetime tau is equal to 1 over lambda, right. So, this is inverse of the decay constant. Now, let us look at some other thing. A particular nucleus, we said decays radioactively, but it can actually decays either through beta decay, okay. It can also possibly decay to other channel, other type of radioactive decays it can undergo. Say for example, if you take actinium which has 89 protons, okay, and with atomic, so the mass number 226, if you take this isotope of actinium, it is observed that it beta decays to thorium 90, okay, and it also undergoes alpha emission to francium with 87 protons in it. Not only that, it can also transform to radium by electron capture. So, all these three types of decays are possible by actinium. Now, for such cases where there are multiple channels, multiple possibilities of decays is possible. So, to get the total probability, you add all these probabilities, which means you have to add lambda alpha, which is the probability per unit time of alpha decay of actinium, add probability of beta decay of actinium, lambda beta, and add the probability of electron capture, lambda epsilon of the actinium, and the total of these will give you the total probability of the decay of radioactive decay of actinium. Again, remember that we are talking about probabilities for these decays. So, when we concentrate or focus on a particular actinium nucleus, it will decay either through beta emission or through alpha emission or through electron capture, or it may not decay for a long time also. But if you take 1000 or some amount of large number of this actinium nuclei, then you will see that the ratio, the number of decays, alpha decays, and the number of beta decays and number of epsilon capture, the electron capture are in these proportions. So, the probability for these to happen are in these proportions. Actually, these probabilities are experimentally measured by looking at the intensity of each of these decay process, the alpha ray, beta ray, and there are ways to work. So, look at the amount of the number of electron capture that can happen. All right. Now, in this particular case of actinium, experimentally it is found that the total decay probability is 6.6 times 10 power minus 6 second inverse or decays per second. So, in 1 million actinium atoms nuclei, then in 1 second 6.6 of this will decay, or in 2 seconds 13 of these will decay. Beta decay probability is about 5.5 times 10 power minus 6, which means out of these 6.6 which decay in 1 second from a sample of 1 million actinium, 5.5 of this is basically beta decay and 1.1 decays through electron capture, or in 2 seconds 2 of this will decay through electron capture, 11 of this will decay through beta decay, and a total of 13 will decay and it is expected that none of these will decay in 2 seconds through alpha decay, because alpha decay probability is 4 orders of magnitude smaller compared to this other two beta and electron capture probabilities. So, if you want to observe alpha decay, you need to actually take a much bigger sample, okay, or wait for a longer time. Now, we have another possibility. The law of radioactivity that we considered, that when one particle decays to another particle, we said the number of particles present in that sample at time t is equal to number of particles present in that sample at time t equal to 0 times exponential minus lambda the time elapsed t. This is true as long as no parent nuclei are added to this. If you add more particles to it, then this decay, this number of particles present at a time t will not be this. So, let us look at such situation. Say, consider case of a series decay, which means you take a nucleus of type 1 denoted by x1, which decays to x2, and x2 is not stable, it decays further to x3. And for a given sample of x1, you start some sample of x1 at t equal to 0, pure x1, no x2 or x3 in it, and you do not add any more x1 type of x1 nuclei into it. So, you just leave it there. What happens? x1 will decay into x2. This follows the radioactive exponential rule that we spelt out earlier. N1 at some time t is equal to N1 at t equal to 0 times exponential minus lambda 1 t, correct. And the number of decays that happens in dt time interval is dN1 equal to minus lambda 1 N1 dt. Now, for the second nucleus, let us see what happens. dN2 is equal to, right, dN1. This would have been the case if x2 is stable. Whatever n1 x1 that decays is converted into x2. So, dN1, which is the number of x1 type of nuclei decayed in dt seconds, dt time, is also equal to the number of x2 type of nucleus present in that sample if x2 is stable. If x2 is not stable, you have to subtract the number of n to x2, which will decay to x3, which follows the radioactive law, which is lambda 2 n2 dt. Okay, let me repeat that. Since x2 is not stable, you have to subtract lambda 2 n2 dt, which is the number of x2 which is decayed to x3, all right, which is equal to dn1 is lambda 1 n1, right, in time dt minus lambda 2 n2 in time dt, or I can write dn2 as lambda 1 n1 minus lambda 2 n2 dt. Note that I have not added minus sign when I wrote dn1, because here we are considering not the number of dn which are decaying. It is true that numerically it is equal to that, but we are actually considering the other way around, saying that what is the number of dn2 which is the number of x2 type of nuclei which are added to the sample, which are produced. So, which is a positive quantity. So, lambda 1 n1 dt, number of x2 type of atoms, nuclei added to the sample in dt time. So, total change in the number of x2 type of nuclei in time dt is therefore lambda 1 n1, the number added, minus lambda 2 n2, the number decayed. All right. So, we can actually write this as dn2 by dt is equal to lambda 1 n1. Now, n1 I can write as n0 e power minus lambda 1 t using the exponential law minus lambda 2 n2, correct. So, to get n2, solve for n2, we will actually put in a trial solution. Let us assume, let us consider n2 equal to a some constant times exponential minus lambda 1 t. It looks like from equation 1 that it has some term which is like exponential minus lambda 1 t, then plus b exponential minus lambda 2 t. This is again expected because there is n2 in equation 1, and n2 itself is expected to also have a decay part, right. It decays to x3, the x2 type of nuclei decays to x3, and therefore, exponential minus lambda 2 t kind of term is also expected in this thing. So, we will take this trial solution. We do not know how much of this is weight factor A and B are, but we will find that now. Putting these two together. So, take our trial solution equation 2, put this back in equation 1, the second term, that will give you dn2 by dt, the first equation, dn2 by dt is equal to first term intact lambda 1 n0 exponential minus lambda 1 t. Second term is minus lambda to n2, but n2 is given by equation 2. Therefore, second part of equation 1 has now two terms, lambda to a exponential minus lambda 1 t and lambda to b exponential minus lambda 2 t. Call this equation 3. We can also get dn2 by dt directly from equation 2, our trial solution. That will give, differentiating the equation 2 will give you dn2 by dt in our on our left hand side, and right hand side is minus lambda 1 a constant times exponential minus lambda 1 t minus lambda 2 b exponential minus lambda 2 t. Now, equation 3 and 4, the right hand side, left hand side is the same. We are talking about the rate of change of n2, that is the number of x2 type nuclei. at some time t in an interval dt, how many of them will change, etc., the rate of change at some time t. So, the right hand side should be the same, right, and right hand side in equation 3 has 3 terms, equation 4 has 2 terms. Okay. So, and the second term in equation 4 and the third term in equation 3 are the same, lambda 2 b exponential minus lambda 2 t. So, when we equate the right hand sides of 3 and 4, we drop these because it is exactly the same and equate the rest, that is minus lambda 1 a e power minus lambda 1 t is coming from equation 4, the right hand side of equation 4, that should be equal to lambda 1 n 0 exponential minus lambda 1 t minus lambda 2 a exponential minus lambda 1 t coming from equation 3. Okay. So, from these two we get, so all of this as exponential minus lambda 1 t as common, take that away, and then you have a equal to lambda 1 over lambda 2 minus lambda 1 times n 0, right. Now, this is one thing. Another thing, so we got A, but what about B? To get B, we will look at another property, which is basically that we took x 1 only, that is we took a pure sample of x 1 type of nucleus to start with. So, at time t equal to 0, n 2 type of x 2 type of nuclei was not present, which means n 2 t equal to 0 is equal to 0. So, from trial solution we get A at t equal to 0, n 2 is a plus b, which is equal to 0, means a plus b equal to 0 or b should be equal to minus a. So, we get both a and b, in fact a and b are simply related with each other by a minus n, and n 2 can be written therefore as lambda 1 over lambda 2 minus lambda 1 times n 0 into exponential minus lambda 1 t minus exponential minus lambda 2 t. So, this is the case of a series decay of x 1 to x 2 to x 3. You can actually consider the exactly similar way other series expansion or any number of such series decays like x 1 to x 2, x 2 to x 3, x 3 to x 4, x 4 to x 5 up to for n, and simply follow this algebra, and then you will be able to get the number of expression for the number of each type of this nuclei at some time t, which can be related with the n 0, which is the number of nuclei of first type, pure sample of n 1 x 1, and with the decay constants of the decay constant of the nuclei involved. Okay. Rate of decay in this case is slightly different. I mean, you cannot write it simply as lambda 2 n 2. Say, in the case of x 1, we can write the activity or the rate of decay as a 1 equal to lambda 1 n 1, because it only decays, nothing is added to it. Whereas, in the case of x 2 type of nucleus, we have a 2 equal to lambda 2 n 2, which is correct, that is the activity that is going on, but that is not equal to d n 2 by dt, because d n 2 by dt has two parts in it. Okay. One is due to the production of X2 type of nucleus coming from decay of X1, and other is reduction because of the activity of X2. Okay. So, but A2 can be written as lambda 2 N2, because the radioactive law always says that activity, the number of particles which is decay, is proportional to N2, number of particles present. That is the kind of observation that we have. So, N2 is equal to lambda 1 over lambda 2 minus lambda 1 times N0 times exponential minus lambda 1 t minus e minus lambda exponential minus lambda 2 t, and from this activity is lambda 1 lambda 2 by lambda 2 minus lambda 1 times N0 into exponential minus lambda 1 t minus exponential minus lambda 2 t. Okay. With this we will stop today's discussion. We will go on with some other properties of the radioactivity in the next lecture.